Hey everyone, Mr. Hauk here. Today we're going to go over the Polar Calculus Day 2 notes. Let's go ahead and get started. So, from our pre-cal days, we have converted coordinates and equations back and forth from polar and rectangular form. This is something most of y'all did back in accelerated pre-calculus last year. Let's go ahead and revisit that real quickly because we can make use of this here in Calc BC. So rectangular coordinates are in the form x comma y, where x is in the independent variable, and polar coordinates are in the form r comma theta, where theta is the independent variable. So formulas that will allow us to convert from polar to rectangular are these two right here. X equals r cosine theta, and y equals r sine theta. Notice that since we have x and y defined in terms of theta, that this means these are parametric equations. Parametric equations. Okay, we also had the formulas that helped us convert from rectangular to polar. R squared equals x squared plus y squared, and tangent of theta equals y over x. For r squared equals x squared plus y squared, taking the square root of both sides, this would also give us r equals plus minus square root of x squared plus y squared. Okay, so let's look at our first example, and then we'll start to actually do calculus things. So in example 1a, we want to convert the polar coordinate 2 comma 5 pi over 6 to rectangular coordinates. So 2 is r, 5 pi over 6 is our theta. If we want to convert it to rectangular coordinates, we know x equals r times cosine theta. So this is going to give us x equals, our r is 2, times the cosine at 5 pi over 6. Well, the cosine of 5 pi over 6 is negative square root 3 over 2. So 2 times negative root 3 over 2, which is negative root 3. Y is going to equal r times the sine of theta. So using 2 and 5 pi over 6, y equals 2 times the sine of 5 pi over 6. The sine of 5 pi over 6 is 1/2, so 2 times 1/2, which is just equal to 1. So 2 comma 5 pi over 6 as polar coordinates will convert to the rectangular coordinates negative root 3 comma 1. All right, example 1b. Let's now convert the rectangular coordinates 3, negative 3 into polar coordinates. So our rectangular coordinates, this is our x and y. Notice that this is also in quadrant 4. That is going to be relevant to us. It's going to be important. So this is in quadrant 4. So what we know we need to get r and theta. R is equal to plus minus square root x squared plus y squared. So r equals plus minus the square root. X squared, 3 squared, that's 9. Negative 3 squared, so the y squared is also 9. So plus minus root 18. Root 18 is 9 times 2, so 3 root 2. Plus minus 3 root 2. Okay. So let's hold on to that r for a moment. Our theta, which is equal to, so up here we have tangent of theta equals y over x. Let's just use that one. Tangent of theta equals y over x. So tangent of theta equals, our y is negative 3, our x is 3, so that's equal to negative 1. So this is going to tell us, well, we want to know, where is theta equal to negative 1? Well, we know that theta is, we know where is tangent of theta equal to negative 1. So we know that tangent is equal to negative 1, at least on our unit circle from 0 to 2 pi. Tangent of theta is equal to negative 1 at 3 pi over 4. and 7 pi over 4. But if you remember, we made note that this point 3, negative 3 is in quadrant 4. Well, 3 pi over 4 is not in quadrant 4. 7 pi over 4 is in quadrant 4, so I'm going to take this with our positive r. Right? So we would have the point positive 3 root 2, comma, 7 pi over 4. Okay, that's our r theta. Now, as we learned in accelerated pre-cal, there are multiple representations of this point. You could also make your r negative and subtract pi from that. That would give you negative 3 root 2, comma, 3 pi over 4. But we're going to stick with that point for right now. Okay? So, the convenient thing to note here, and we noted it right up here, is that the conversions from polar to rectangular form are essentially a way of parametrizing the curve. Okay? These are parametric equations. R and y are in terms of theta. Okay, just like previously we had, sorry, not r and y, x and y are in terms of theta. Just like previously we had x and y were in terms of t when we were looking at parametric equations. Okay, so we can now have two equations that describe the x-coordinate and the y-coordinate. We can use the same ideas that we did for parametric calculus, and now we can apply some calculus things. So, if we want to find the slope of a polar equation, so we're going to turn this into a flashcard. To find the slope of a tangent line to a polar graph r equals f of theta, we can use x equals r times cosine theta and y equals r times sine theta as the parametric equations. So we're going to have x and y be defined in terms of the variable theta. So dy dx, the slope, will be the same as y prime of theta, or dy d theta, over x prime of theta, or dx d theta. And the way that we're going to find that is because we're going to be taking the derivative of x and y with respect to theta. Okay? So y here, for example, is r times the sine of theta. Now here's the tricky part. R itself is a function of theta. Okay? R itself, this piece right here, is a function of theta. And sine of theta is a function of theta. So when we try to take the derivative of y, we have, and y is a function of theta times another function of theta. Well, if I want to take the derivative of a product of two functions, I'm going to have to apply the product rule. Okay, we're going to have to apply the product rule here. So let's think about this. If I take the derivative of y with respect to theta, again, r itself is already a function of theta. So product rule says, take one function, leave it alone. Okay, so r times the derivative of the second function. Well, the derivative of sine of theta with respect to theta is cosine of theta, plus the second function left alone, sine of theta, times the derivative of the first function. Well, the derivative of r would be r prime. Okay. Now we're going to do the same thing. We're going to take the derivative of x with respect to theta. Okay, derivative of x with respect to theta. So same deal. X is r times cosine theta. R itself is already a function of theta. Cosine of theta is a function of theta. So we're going to have to apply product rule when we take its derivative. So using product rule, first thing, r times the derivative of the second function, well, derivative of cosine of theta is negative sine of theta, plus that second function unchanged, cosine of theta, times the derivative of the first function, derivative of r would be r prime. Okay? So this is the formula to find the slope of a tangent line to a polar graph. Okay? This is what we're going to turn into a flashcard. So let's try it out. Let's put this to work here. Example 2, find the derivative dy dx of the graph of the polar curve r equals 2 plus 2 sine theta at theta equals pi over 2. Then write the equation of the tangent line at theta equals pi over 2. All right, so first things first, let's go ahead and get our derivative. So dy dx equals dy d theta over dx d theta equals, okay, well, dy d theta, remember y is r times the sine of theta, okay? So r itself is 2 plus 2 sine theta, okay? R itself is 2 plus 2 sine theta. So we have to find dy d theta. So let's just go ahead and say, let's make some notes off to the side here. Let's go ahead and get x and y. So x equals r times cosine theta, which is, if we do r times cosine theta, that's 2 plus 2 sine theta, that's r, times cosine theta. If we go ahead and distribute the cosine theta, like so, that's going to give us 2 cosine theta plus 2 sine theta cosine theta. Right? Y is r times sine theta. Well, again, r is 2 plus 2 sine theta times sine theta. Distribute the sine theta, we're going to get 2 sine theta plus 2 sine squared theta. Right? So we are taking the derivative of y with respect to theta. So we're taking this derivative right here, and this 2 sine squared, let's go ahead and write this as 2 sine of theta squared. Just a little nicer for when we take its derivative. So dy d theta. Okay, well, taking the derivative of this thing here, the derivative of 2 sine theta is going to be 2 cosine theta plus derivative of 2 sine of theta squared. Well, the inside function here is sine of theta, so this is going to be chain rule with power rule. 2 times 2, that's going to be 4. Keep the inside the same, sine of theta. Reduce the exponent down by 1. Then multiply by the derivative of the inside. Derivative of the inside is cosine. So 4 sine theta, cosine theta. All right, so there's the derivative of y with respect to theta. And now we're going to find the derivative of x with respect to theta. Well, we have x right here in terms of theta. The derivative of 2 cosine is negative 2 sine plus 2 sine cosine. Taking that derivative is going to be product rule again, okay? Sine of theta is a function of theta, cosine of theta is a function of theta. Taking the derivative of the product, we're going to use product rule. So first function the same, 2 sine times the derivative of the second one. All right, so the derivative of the second function, derivative of cosine is going to be negative sine plus second function, 2 sine cosine. Or sorry, second one is 2 cosine times the derivative of the first, which is going to be just cosine. Derivative of sine is just cosine there. Okay. We can clean this up a little bit. Let's clean this up some. 2 cosine theta plus 4 sine theta cosine theta over negative 2 sine theta minus 2 sine squared plus 2 cosine squared. Okay, so we've got our derivative function. got our derivative function here. And we need to calculate, because we're trying to find the equation of the tangent line at theta equals pi over 2, we need to calculate our derivative, dy dx, such that theta equals pi over 2. All right, so plugging in pi over 2, well, cosine at pi over 2 is 0, so this is going to be 2 times 0 plus 4 times, let's see, sine at pi over 2 is just 1, and cosine at pi over 2 is 0 over negative 2 times 1 minus 2 times 1 squared plus 2 times 0 squared, and that's going to equal 0 over, looks like negative 4, which is just 0. All right, so that's our slope. This is our m. All right, we also need the x and y at theta equals pi over 2. So let's go ahead and calculate those real quick. X at pi over 2 equals, so we got the function right here. Cosine at pi over 2 again is 0 plus 2 times 1 times 0. So that equals 0. Y at pi over 2 equals 2 times 1 plus 2 times 1 squared. That's going to equal 4. So the equation of our tangent line, we have our x, we have our y, we have our slope. Equation of the tangent line is going to be y minus 4 equals 0 times x minus 0. And of course we should clean that up. This just gives us y equals 4. Okay. Now, a couple things to notice. You know, we spent some time up here deriving this formula for slope of a polar equation. Notice that what we did here in this example is we went ahead and found x and y in terms of theta already. So we didn't need to sit there and we didn't really follow this formula because we already had x and y in terms of theta. And that's what we were having here. You know, dy dx was dy d theta divided by dx d theta. So we could just go ahead and calculate dx d theta and dy d theta because we already had x and y in terms of theta. Okay, so this particular formula, you honestly don't really need to memorize it all so much as be able to reproduce it. Okay, be able to derive it. Let's try example 3 here. Find the points r comma theta of horizontal and vertical tangency to the graph of r equals 2 cosine theta between 0 and pi. Notice that pi is not included in the domain, okay, but 0 is. So this, make sure we pay attention to our domain. Here's what I'm going to do. Instead of finding the points r comma theta, I'm going to go ahead and find the thetas, and you could find the r's by plugging theta back in and solving for r. Okay, so I'm going to find the thetas. But looking here, we need to find, I'm going to try to find the thetas where we have horizontal and vertical tangencies. Okay, remember, when we think horizontal tangency, we want to be thinking dy dx equals, which is dy d theta, over dx d theta. But when we think horizontal tangency, we want to be thinking 0 over some non-zero value. And when we think vertical tangency, we want to be thinking dy dx, which again is dy d theta over dx d theta, is some non-zero value over 0. Okay, remember that's what we want to be thinking when we see horizontal and vertical tangency. So what I'm going to go ahead and do to find the angles, the theta, where we're going to have horizontal tangency, I want to know when dy d theta is equal to 0. And to find the thetas where we have vertical tangency, I want to know when dx d theta is equal to 0. Okay? So let's go ahead and do that. To find dy d theta and dx d theta, we should probably go ahead and find x and y in terms of theta. So x in terms of theta is r times cosine theta. R itself is 2 cosine theta, so this is 2 cosine theta times cosine theta, okay, which is 2 cosine theta squared. Y, which is r times the sine of theta, well, again, we already know r is 2 cosine theta, so 2 cosine theta times sine theta. That's going to be our equation for y. All right, so horizontal tangencies, let's deal with that first. To find the thetas where we have horizontal tangencies, we want to say dy d theta equals 0. This implies that 2 cosine, well, first off, we need to find dy d theta. Okay, so let's go ahead and take the derivative of this, which is going to be product rule, right? That's going to be product rule. So let's figure that out. Dy d theta equals first function, 2 cosine theta, times the derivative of the second function. Well, the derivative of the second function, sine theta, is cosine theta, plus second function, sine theta, times derivative of the first function. Derivative of the first function, 2 cosine theta, is negative 2 sine theta. And if we clean this up a little bit here, this is 2 cosine theta squared minus 2 sine theta squared. All right, so there's our dy d theta. We want to know when this is equal to 0. Okay, so dy d theta equals 0 means that, oh, I got plenty of room, means that 2 cosine theta squared minus 2 times sine of theta squared equals 0. This means I can go ahead and add the 2 sine theta squared over to this side on the right. So 2 times cosine theta squared equals 2 times sine of theta squared. You can eliminate the 2's here, divide each side by 2. So in fact, let's actually do something a little bit different. Let's do this. Let's divide both sides by 2 times cosine theta squared. All right, on the left side, that's going to give us 1. On the right side, the 2's will cancel. Sine squared over cosine squared is tangent squared. Okay. This would also, if we take the square root of both sides, this would tell us the tangent of theta is plus or minus 1. And we know that tangent of theta on the interval 0 to pi, not 0 to 2 pi, but 0 to pi, we know tangent of theta is positive or negative 1 on the interval from 0 to pi at pi over 4 and 3 pi over 4. Can't go anything past 3 pi over 4 because that would take us outside of our domain. Okay, so those are going to be the two angles theta where we have horizontal tangency. Vertical tangency, which is going to work the exact same way. Only this time, we're concerned with the x d theta being equal to 0. All right, well, let's go ahead and figure out what the x d theta is going to be right here. So the derivative of 2 cosine theta squared, again, this is going to be chain rule with power rule. The outside function is stuff squared. The inside function is cosine theta. So applying power rule, 2 times 2, that's going to give us 4. inside function cosine theta, reduce the power by 1, times the derivative of the inside. Well, the derivative of the inside is derivative of cosine theta is negative sine theta. Okay, so this is negative 4 cosine theta sine theta. So saying we want to find where dx d theta is equal to 0 is the same as saying when it's negative 4 cosine theta sine theta equal to 0. Okay, well, on the interval from 0 to pi, again, it's 0 to pi only. On the interval from 0 to pi, if either cosine or sine is 0, then of course their product is going to equal 0. So sine or cosine is equal to 0 from 0 to pi when theta equals 0 or pi over 2. Okay, again, if you wanted to find the r's, I know the problem says find all points r comma theta. You can simply take your thetas and plug them in to get r. Okay, but I'm going to go ahead and move on to the next problem. All right. Next little topic here is arc length of polar curves. We're again going to go ahead and turn this into a flashcard. So flashcards so far. This one. This one, slope of a polar equation. This would be a good flashcard. All right, so arc length of polar curves. So we've already seen arc length. We've seen arc length of parametric curves. Now we have arc length of polar curves. This is going to be our third arc length formula. The length of a curve with polar equation r equals f of theta over the interval from alpha to beta is given by the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. All right, so calculator active. Find the length of the curve r equals 2 minus 2 cosine theta over the interval from 0 to 2 pi. Well, it's calculator active, so we just need to make sure we set it up correctly and we enter it in the calculator correctly. So our arc length, L, equals the integral from alpha to beta. That's the interval. Okay, our interval is 0 to 2 pi. So integral from 0 to 2 pi of the square root of r squared. R is 2 minus 2 cosine theta. So 2 minus 2 cosine theta squared plus the derivative of r with respect to theta. Let's go ahead and calculate that. Calculate that right here. Dr d theta equals, well, derivative of 2 is 0. Derivative of negative 2 cosine theta is 2 sine theta. All right. So dr d theta, that's going to be 2 sine theta, all squared, d theta. Go ahead and plug this into your calculator, Math 9. I would try to show it on here, but since I'm recording on an iPad, I don't have the TI-84 software on here. So go ahead and try it yourself. When I plugged it into my graphing calculator, I ended up getting 16. So take a moment and go ahead and try that out. Pause the video if you need to. That's what I got right there. All right. Now let's try one that's not calculator active. Find the length of the curve, r equals 2 cosine theta over the interval negative pi over 2 to positive pi over 2. All right. So let's go ahead and set it up. L equals, the interval is negative pi over 2 to positive pi over 2. Square root r squared, so 2 cosine theta squared, which would be 4 cosine squared, plus, let's go ahead and get our derivative, dr d theta equals, well, the derivative of 2 cosine theta is going to be negative 2 sine theta. All right, so if we square that, so dr d theta squared, we're going to get 4 sine squared of theta d theta. There's a cool little property that's going to apply. Hopefully you see it. If you don't, we'll see in just a second. I'm going to factor out the 4. And pause the video for a moment if you don't see it. Try to figure it out. But there's a nice little identity from pre-cal that is going to simplify this quite a bit for us. And that identity is that cosine squared plus sine squared is equal to 1. So now we have integral from negative pi over 2 to positive pi over 2, square root of 4 d theta, which is obviously integral from negative pi over 2 to pi over 2 d theta. We can very easily take that antiderivative. The antiderivative of 2 is 2 theta. And we're going to evaluate from negative pi over 2 to positive pi over 2. So evaluating at the upper bound first, 2 times pi over 2, that's just pi, minus evaluating at the lower bound, 2 times negative pi over 2, that's just negative pi, and then pi minus negative pi equals 2 pi. Very nice. All right, so you'll see some questions like that probably where we do arc length of polar curves. Now, our next topic in the notes is a pretty jam-packed set of notes. We've got derivative, slope of a polar equation to help us find equations of tangent lines. We've got arc length of polar curves. And the last topic we're going to talk about today, and we're going to expand on in the next set of notes, is polar area. So we're going to look at areas enclosed by curves. Keyword though, enclosed, not under. These work a little differently than other area formulas that we've done or other area calculations we've done. The formula for polar area is different from all previous area formulas because it's not based off of rectangles. Remember, when we were doing area under the curve, we were summing up these infinite numbers of rectangles. Well, what we're going to do instead is we're going to sum up a bunch of sectors, essentially. So instead, polar area uses an infinite number of infinitely small sectors to find the area. So instead of rectangles, we're using sectors. From geometry, we know the area of a sector of a circle is given by the equation A, that's area, equals 1/2, whatever the angle is, times the radius squared. Okay? Where theta is measured in radians, our area of interest is contained between the angles alpha and beta. Okay? So let's say we had some polar curve generated by r equals f of theta, so r is a function of theta, and alpha to beta are the angles that we're interested in. Well, let's think about the area of a single sector. Okay? Area of a single sector. Well, we know the area of a sector is 1/2 theta r squared. Now the thing is this theta, we're going to be taking the sum of infinitely small sectors, okay? So when we think about a small sector now, this theta is going to be getting smaller and smaller. We're going to think of this as d theta, kind of like we looked at dx as that little width of those rectangles, okay? So we're going to be looking at it like this now. This will be 1/2 r squared d theta, all right? Now, if I wanted to find the area of infinitely many little small sectors, so area of this sum of small sectors, think of it an infinite sum of infinitely small sectors. Well, we know that to do an infinite sum, we would use definite integral notation. So from alpha to beta, so the integral from alpha to beta, 1/2 r squared d theta, okay? Of course, the 1/2 being a constant, you could pull to the outside, which is what I'm going to do many times. Remember, R is a function of theta, d theta, okay? This, I would go ahead and make a flashcard, another flashcard. Okay, so polar area, we use the integral from alpha to beta 1/2 r squared d theta. All right, that's going to be another flashcard. So let's try a problem. And for these problems, for almost the rest of the problems, we're going to make the majority of them calculator active. Let's go ahead and make example 5 calculator active. All right, so example 5. Find the area bounded by the graph of r equals 2 sine theta. Notice that this is a circle. We talked about this in the previous set of notes. This is the setup for a circle. This circle has, in particular, diameter 2. Not radius 2, but diameter 2. Also remember from yesterday that when we graph circles, we only needed a domain of 0 to pi to produce the graph once. So, to find the area of this circle, find the area bounded by the graph of r equals 2 sine theta, that's the circle, the area is going to equal from 0 to pi, integral from 0 to pi, 1/2 times our function of theta, which is 2 sine of theta, squared d theta. Okay? Integral from 0 to pi, 1/2, 2 sine of theta squared d theta. Again, this is calculator active. Go ahead and put this into Math 9. Pause the video if you need to. Go ahead and calculate that. Okay, what I got when I calculated it, I got pi. Now, we actually didn't need to do that. We can use what we already know from geometry to solve this problem as well. Again, if you recognize the format of the equation, the format of the polar equation, again, this is a circle with diameter 2. Well, from geometry, we know area of a circle is pi times the radius squared. Well, if the diameter is 2, then the radius is 1. Pi times 1 squared is just pi. You get the same exact answer. Okay? So we could use that little bit of knowledge from geometry if you can recognize that you're dealing with the equation of a circle. All right, let's try a few other area problems. So last page of our notes here. Example 6, find the area bounded by the graph of r equals 2 plus 2 cosine theta. This is not a circle. And in fact, what I would encourage you to do is again, I can't really show it because I'm using an iPad, so I can't pull up the TI software. But this is, if we graph this, and again, I know, I'm going to use Desmos. I know that we can't, Desmos isn't allowed on the AP exam, but just for visual sake. So we have r equals 2 plus 2 cosine of theta. Okay, and notice that this graph is going, to generate this graph, we have to go from 0 to 2 pi. If I only go 0 to pi, for example, it's only going to generate half the graph. So I'm having to go the full 0 to 2 pi. Okay, so we want to find the area of this polar curve. So area is going to be, and I'm going to pull the 1/2 out this time, 1/2 integral 0 to 2 pi, our function r of theta, so r of theta squared, 2 plus 2 cosine theta, squared d theta, It's calculator active, so go ahead and pause the video if you need to. Take a moment, plug this into your calculator, use Math 9. I ended up getting 18.850. Okay. In example 7, find the area of one petal of r equals 2 sine 3 theta. So things that we already talked about, in the last set of notes. This is going to make a rose curve. Because the coefficient of theta is odd, we know that that odd coefficient 3 is the number of petals that we're going to have. Again, if we need a visual, use your TI-84. Again, I don't have the TI-84 software in here, so I'm going to use Desmos. But let's go ahead and graph it to get a nice visual. R equals 2 sine of 3 theta. 2 sine of 3 theta. And we can see our rose curve with 3 petals. Okay. Now, we want to find the area of a single petal. So if you remember from yesterday, one way that we can single out a single petal is to figure out what are the angles theta where the curve hits the pole. And to find out where the curve hits the pole, we set r equal to 0. Okay, so what I'm going to do, I'm going to set r equal to 0. This means 2 sine of 3 theta rather, equals 0. Well, I'll divide 2 on both sides. This means sine of 3 theta equals 0. And we know that sine of theta equals 0 at 0, pi, 2 pi, 3 pi. So 3 theta equals 0, pi, 2 pi, 3 pi, dot, 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 on in that order, which means theta itself, if we divide all those by 3, is equal to 0, pi over 3, 2 pi over 3, 3 pi over 3, which is pi, dot, dot, dot. And we talked about this in the previous set of notes. If we take any two sequential, like any of these two that are next to each other, like 0 and pi over 3, these would result in one petal. 0 to pi over 3 would make one petal. Okay? So to find the area of a single petal, we're going to use any two sequential angles like that, and we are going to have those be the lower and upper bounds. So our area equals 1/2 times the integral 0 to pi over 3. And let's go ahead and make sure, by the way, let's verify that that makes one single petal. So Desmos, again, you could do this in your TI by adjusting the window. You can make your table, your theta minimum 0, make your theta maximum pi over 3. And we can see that we're going to get one single petal. Okay, so 0 to pi over 3, we get a single petal of, and then we're going to have our function 2 sine of 3 theta squared d theta. So 1/2 integral from 0 to pi over 3, 2 sine of 3 theta squared d theta. Go ahead and plug that into your calculator. I ended up getting 1.047. All right, 2 examples to go. Example 8, write an integral expression that represents the area of one petal. So again, we're going one petal here. And we are not solving this problem. We are just writing the integral expression. However, we could solve it pretty easily because if it was calculator active. So again, we want to find an area expression for one single petal. I'm again gonna look at where this curve is gonna reach the pole. So r equals 0. This implies that 4 cosine of 2 theta equals 0. Divide 4 on both sides. Cosine of 2 theta equals 0. We know that cosine is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2. Okay, so 2 theta equals pi over 2, 3 pi over 2, 5 pi over 2, and so on. Dividing everything by 2, we have theta equals pi over 4, 3 pi over 4, 5 pi over 4, and so on. Okay, one single petal. I'm just going to use the first two, pi over 4 to 3 pi over 4. All right, so this is going to generate one petal for us. So the area of a single petal, area equals 1/2 integral pi over 4 to 3 pi over 4 of 4 cosine 2 theta squared d theta. Right, so there's an area expression that will do exactly what we want it to do. And then our final example denotes, find the area inside one loop of r squared equals 4 cosine 2 theta. All right, so again, we're talking one loop. Right, r squared equals 4 cosine 2 theta. Again, I want to figure out when is this thing going to, when is our curve going to hit the pole, okay? So, let me do this and keep it consistent with the colors here. So I want to know, when will 4 cosine of 2 theta equals 0? This means when will cosine of 2 theta equals 0? We pretty much just did this a moment ago, right? Cosine of 2 theta equals 0, pi over 4, 3 pi over 4, so on and so forth. Okay, so our area of one single loop is 1/2 integral. Again, pick two next to each other. Pi over 4 to 3 pi over 4. Of our function, 4 cosine of 2 theta squared. D theta. Well, actually, hold on. We got to be a little bit careful here. 4 cosine 2 theta is r squared. We do not need to square this again. Okay, little bit tricky there. Let's make note of that. This is r squared. 4 cosine of 2 theta is r squared. We don't want to square it again. We'd be getting the wrong thing. We'd be doing the wrong calculation. Let's go ahead and make this calculator active just because the video has already gone on long enough here. When you go through, I believe when you plug this in the calculator, you end up getting -2, but we're talking about area here. So the area is equal to 2. Right. So that covers it for this video. In the next set of notes, we're going to be having polar curves, 2 different polar curves intersect each other, and we're going to be trying to find different kinds of areas, like areas of overlapping regions or areas of little loops, things like that. Right.